In this video, just like we did for the exponential function and the sine and cosine functions, we're going to take a look at the graph of the logarithmic function, the natural logarithm, and see if we can come up with a rule for its derivative just by zooming in at various points. And so let's head over to GeoGebra. All right, so here is the natural logarithm function. And one thing to notice here as we look at the natural logarithm function is that it's only defined for values of x that are greater than 0. All right, so that is important to us. We'll talk about negative values in a little bit. All right, so let's home in here at our x value of 1. And what do you spot about the slope of this function? So the slope here is equal to 1. So something you might want to do is you might want to pause the video right now, head over to GeoGebra, create this function, and look at other points and see if you can come up with a rule yourself. All right, everybody who's here, I am expecting has either done that or decided they're not going to do it. So we're homing in here where the x value is equal to 2 here. Just kind of zooming in until we get some good, at least pretty close to precise grid points. So over here, I've got two, close enough for me points. And so we're going up 1 and over 2. So the slope here is equal to 1/2. All right, let me skip over. I'll do 4. We don't need to do things in the precise order. All right, here's a good solid grid point. So we're going up 1, 1, 2, 3, 4. So when x was equal to 1, the slope was 1. When x was equal to 2, the slope was 1/2. When x was equal to 4, the slope was 1/4. So that's starting to be a pattern. Why don't we look over here where the slope is 1/2? I think I'm expecting, what do you think I'm expecting to find here? I think I'm expecting to find a slope of 2. Let's see if we succeed at that. Searching for a good grid point. It is taking its time. Come on, natural logarithm. Here we go. All right, so up 2 over 1. So this looks like we've got a solid rule here. And we'll verify some of these principles later on in the year when we've got a few more tools in our toolbox. We'll be able to go back and say, yeah, the derivative of the natural logarithm is just what we thought it should be. But let's take a look at the sheet that I came up with here. So heading off to the document camera. So what we have based on this is that the derivative with respect to x of the natural logarithm of x is 1/x. And like we saw from this graph, this is only true when x is greater than 0. If we want to think about all values of x positive or negative, we need to think about the function, the natural logarithm of the absolute value of x. This will be important to us in the spring when we start talking about integrals. But for the time being, we don't need to worry about the absolute value of x when we take logarithms. And the same thing happens, I'm not going to look at it, when we take the logarithm to other bases. Just like we did with the exponential, the expression is 1/x, but then there is this scaling factor of natural logarithm of a in the denominator that changes it, which once again makes the natural logarithm, it's well named. It is the most natural of logarithms because it's the one that doesn't have this extra scaling factor in it. Okay, so this has started to give us a good collection of derivative functions. Let's take a look at this, which is the reference sheet for derivatives and limits. I have shared this with you before. Yeah, I got the glare going on here. So we'll look at the common derivatives and we'll see some things that we've already figured out. So the derivative with respect to x of x is equal to 1. The derivative with respect to x of sine x is cosine x. The derivative with respect to x of cosine x is negative sine x. We'll work out the rest of the trig functions in a couple videos after we work out some extra rules. The inverse trig functions, I'm not sure we need to worry about it, but I'll figure that out and let you know later. We see that the derivative with respect to x of the exponential function is the exponential function, like we saw. When we've got the derivative with respect to x of a different exponential function, it's a to the x plus the scaling factor of the natural logarithm of a. And then these last three rules are what we just came up with in this video. That the derivative of the natural logarithm is 1 over x when x is greater than 0. To deal with positive and negative values, we need the natural logarithm of the absolute value of x, and arbitrary logarithms have this extra scaling factor depending on the base that we come up with. So we're starting to build up a significant toolkit of derivatives. So that's going to give us some power to work with more complex functions, but we need a few rules in order to process more complex functions based on these elementary functions. And that's what we'll head our attention to very soon.